In this video, I'm going to be discussing oscillatory motion. Oscillatory motion can be termed as the repeated motion in which an object repeats the same movement over and over. In the absence of friction, oscillatory motion would continue forever, but in the real world, the system eventually settles into an equilibrium. So, for example, I could be using a pendulum clock because it just goes back and forth, the motion of a swing because it just goes back and forth, or even birds' wings flapping. This all is to remain constant in a period, and the frequency is defined as the number of events per unit of time. Below, I will show two examples that identify the problems completely with diagrams and explanations of the thought process I used to solve the problem and why I selected the problems and some assumptions I made. So for my first problem, a 0.75 kilogram block is vibrating according to the equation x equals 0.65 cosine 7.35 t. Determine the amplitude, frequency, period, and Franck's constant. So right here, this is just an example where I'm like, okay, so for if this is 1.5, this is going to be 1.5. So the free amplitude is the highest it can go, and if the highest it can go is 1.5, the lowest it can go is negative 1.5, and that's like the max interval. So when I plug it in, the x equals a cosine wt, this is already done. So 0.65 is the amplitude. Therefore, that is part A. And when you actually look closer, W is in there as well. So W is 7.35 T. So when I go down here more, continuing, so to calculate B, which is the frequency, you need to do W equals 2 pi F. When you divide 7.3 pi by 2 pi, you get 1.17 hertz as the frequency. The period is only 1 over the frequency, so therefore that is an easy calculation. So you just put 1 over the frequency, 1 over 1.17, and you get 0.855. Now, you can actually graph this. So from where you're at right here, so the period is one of these, and the period is 8.55. So right here, this is the halfway mark, which is down there and everything. And then here's the amplitude, the top and bottom on how far it goes. So that's part 3. Now there's one more. We got to calculate the spring constant. So 2 pi f equals 1 over 2 pi, and then the square root of k over m. You multiply by 2 pi to get rid of that. You get 2 pi f squared, and then you continuously move down. M 2 pi f squared time equals k, and then you just plug and chug, and then you get down to the mass times the W squared, which comes out to 40.52 and newtons per meter. Now, for my next question, it involves the force of 500 newtons is used to stretch a string that has a 5.5 kilogram block attached to it, and it moves it by 0.35. What is the spring constant value, and calculate the frequency of the oscillator? So as I drew right here, this is just the initial spring. This is how much further it moved from here to here with 500 newtons of force. and the main things we're going to use for part A is F equals kx for the spring constant. And then for part B, we use F equals 1/2 pi square root k over m. So whenever I plug and chug, all over here, the spring constant value is 500 newtons over 0.35 meters, and that comes out to 1428.6 newtons per meter for the spring constant value. And the frequency is 1 over 2 pi times k square root k over m, and this equals 8.51 hertz for the frequency. So that answers those questions. And then, so the difficulties I found making sense of the problem is, for the first problem, I had trouble making sense of the periods, so I wasn't completely sure how to do this. So I had to divide by 4 for the first one, I had to divide by 2 for the second, and I had to multiply by 0.75 to calculate the 3 spots of the numbers where these are going to be placed. It's not part of a question, but it's good to know where everything is going in the graph, because it's harmonic motion and it's repetitive, so it just keeps on going and going and going until it stops at an equilibrium. Include your self-assessment. I think I did okay in this. I didn't do the best. And that's everything. Thank you.